Hello, good morning, dear participants. Welcome to the fourth International Congress on Human-Computer Interaction Optimization and Robotic Applications. FORA 2022 is organized by National Technical University, Kharkiv Polytechnic Institute from Ukraine. FORA 2022 is technically sponsored by IEEE Turkey section. Thank you for your scientific contribution and support to FORA 2022. Let's issue one start the session. First paper belongs to dear Ying Li. Dear Ying Li, are you ready to present?
Yes, I'm Ying Li. Yeah.
Okay, you can start your presentation if you are ready.
Okay, can you hear me?
Yes, please, you have 10 minutes.
Oh, okay. Could you see my slides?
Yes.
Hello? Oh, okay. Good morning, everyone. It is my pleasure to participate in the conference. My talk today will deal with the topic of multidisciplinary evaluation metrics for the usability of wearable chairs. My talk will be in 4 parts. First of all, I will be presenting the background. Then I will explain why we need to attention to this issue. After that, I will introduce the method and metrics that we proposed. And the last part is the conclusion. Now let's turn to the first part. As we can see, these images show factory workers at work. Generally, they work 8 hours a day, which means they have to awkward positions on time. And this condition can easily lead to one kind of disease, musculoskeletal disorders, and can occur in any part of the human musculoskeletal system. And the main work factors causing work-related musculoskeletal disorders were repetitive work or long-term working in awkward or tiring position. According to HSE statistics, long-term standing work can cause musculoskeletal disorders of the upper back and lower extremities, and accounted for 44%, 37%, and 19% respectively. Although these diseases are rarely life-threatening, they influence the quality of life of most patients. The good news is the rate of work-related musculoskeletal disorders shows a general downward trend, although it has fluctuated throughout the years. This may be related to the research and development of wearable exoskeletons, and some industrial exoskeletons have tried to be used in manufacturing production environments. As we can see from the picture, the sitting exoskeleton robot is an auxiliary device that can provide sitting assistance and has proved to reduce the muscle fatigue of workers' lower limbs. However, some scholars have proposed the phenomenon as follows in their research. First, the advantage may be diminished. Second, user experience is significant. So, in practice, a good performance in some aspects doesn't mean that it also has good usability throughout the use of process. Therefore, it is crucial to define the methods and metrics for the comprehensive evaluation of wearable chairs. And what we hope is from the human-centered perspective, let's make the code machine have more temperature. Well, now we come to the next point, which is the research status of sitting exoskeletons. As I list, current research focuses on the evaluating the functional performance of wearable chairs in simulated work experiments. However, in practice, the product's effectiveness in a specific task doesn't mean that it also has good usability in the entire use process. So, based on the theory of usability, we propose it's necessary to consider the representative users' behaviors in the practical scenarios, which means the usability metrics of wearable chairs in multitasking need to be considered. Generally, the use process of wearable chairs includes putting on to starting work. They are maybe working in different sitting heights or walking states, finishing work, and taking off the equipment. So we propose the multidisciplinary evaluation methods, which contain 3 modules of testing: wearing, walking, and simulated work. The figure below shows the evaluation system. The system combines knowledge from multiple disciplines, such as ergonomics, kinematics, user experience, and so on, and proposes 4 types of evaluation metrics: physiological parameters, kinematic parameters, objective performance indicators, and subjective evaluation indicators. The point to note is that in the above evaluation to each indicator, because when wearable chairs using different fields, the importance of each type of evaluation metrics is unequal due to the evaluation purpose. Therefore, researchers can adjust the weight of each metric according to the actual situation. Additionally, not every metric exists in different experimental modules. They are all essential. When it comes to the physiological parameters, they are often used to reflect the user's physiological fatigue state. The Merriman metrics may include electromyography, respiration, heart rate, and so forth. And kinematic parameters are ordinary in the evaluation of the exoskeleton because walking assistance is not a wearable chair's core function. We only focus on the stability and giant balance when wearing it to explore whether the equipment will interfere with the user's walking and the degree of interference. As for the objective performance indicator, not each one does apply to all products. It's necessary to select or set objective indicators according to the specific experimental purpose. And subjective evaluation indicators directly feedback the opinions of users. So this paper mainly put forward 3 representative subjective questionnaires. Researchers can also choose other reliable and effective questionnaires according to the purpose. The above are 4 types of indicators in our proposed evaluation system, and all the Merriman indicators are in this table. And compared with the existing research, the proposed multi-model Merriman is the first attempt in wearable chairs based on ergonomics, user experience, and other perspectives to obtain more effective evaluation information. However, the above process is in general. It doesn't take into account emergencies in practical applications. Thus, it's an idealized laboratory evaluation and may vary from the field evaluation. Usability testing that simulates real-world emergencies can be supplemented in the future research. In conclusion, We hope that the paper could provide a reference for future studies and promote the discussion of the lack of systematic evaluation methods for such industrial exoskeleton, and the wearable equipment could be more safely, effectively, and efficiently used in future actual work scenarios. Let's make the code machine have more temperature together. And that's all I want to say. And thank you for taking the time to listen to my presentation. So if you have any questions, you can ask me. Thank you.
Thank you for your presentation. Dear participants, do you have any question about the paper? Okay, no questions. Thank you again. I wish you success in your career. Next paper belong to
Okay.
dear Yunus Al-Safar. Are you ready to present?
Yeah, yes, I am ready.
Okay, you can start if you want.
Yeah.
You have 10 minutes, please.
Okay. Good morning, everybody. Do you hear me? Can I start?
Yes.
Yeah. Our paper is talking about design of near-infrared bandpass multi-layer thin film filter. So we'll design and fabricate a filter working in the near-infrared bandpass filter. Motivation. A near-IR filter have a vital role in many different systems and applications, such as imaging system, thermal imaging, target identification, detection of some disease, remote control, and etc. So all these applications need working with infrared. So we need infrared filter to optimize the application work. The introduction. A new technique have been utilized with using emerging material of new optical, electrical, and electric properties toward producing a new device with a new function that could be used in many applications. Thin film are part of these applications that are influenced by new technology. The fabrication is difficult for the near and mid-infrared optical filter because when the band be near to the visible region, the fabrication will be difficult. But for the far infrared region, the fabrication and design will be sometimes low difficulty than the near infrared filter. In general, optical filter in the infrared range are very beneficial due to their broad range of applications such as imaging devices. Methodology. In this work, multi-layer thin film working at near infrared range, 3 to 5 micrometer was designed and investigated. So we design and make the design in one software and investigated our design in another software. And as we will see in the next slides. The proposed structure was efficient and reliable as a near filter, which have vital role in many systems and different applications, such as imaging system. Here is the general design. As we see here, with the general design is we have substrate from zinc selenide material and coated with two coats, the coating A and the coating B. The incident light will be here, and the existing light will be from this place. So this is the general design for the near filter. The coating A is the side which is the incident for the IR, while the coating B is the existing side of the IR. We also call the coating A in the front layers, and we call the coating B in the back layers. Both coating A and coating B contained from multi-layer structure, from multi-material, from two material, one with high refractive index and another with low refractive index. One material with high refractive index and another material with low refractive index to assume reflection or refraction at the boundary between the two materials. We will go in full details in next slide here. So here, the high refractive index, we choose it from the gallium arsenide, and the low refractive index chosen from the magnesium fluoride. As we see in this picture, there are a difference between the refractive index in the two materials because we need this difference to make the IR refraction or refraction from at the boundary. Here's the full design in full details. This is the coating A and this is the coating B. As we see, the coating A contains from many layers, but the layer began the numbering for the layer began from the substrate and so on. So for the coating A will be from 1, 2, 3, 4, and so on. And for the coating B, we will begin from the substrate here for the first layer, second layer, third layer, and so on. The IR direction will be from top to bottom. As we see here, the incident light will be here, the infrared, and exists from this region. For coating A, the infrared flow from the last layer to the first layer, then substrate. And for coating A, the IR flow from the first layer toward the last layer. So this must be taken in your consideration for the IR direction flow. So for designing any multi-layer structure filter, we must test the material using in the filter. So we have the substrate from the zinc selenide, and we have two material for the coating A and coating B, which is the gallium arsenide and magnesium fluoride. So we must test these material, which are the base for the filter. This material must have good transmittance for the IR band. So we put this in the program and make tests for them. So we found that these material are good transmittance for the IR band. After choosing the material and selecting filter bandpass range of wavelength, we start with our designing. So first design was for IR filter working in the near infrared region with 12 layer only. So this is the response. As we see here, from 3 to 5, we have good transmittance, but we still have unwanted peak here and unwanted peak here need treatment. So we make optimization for our design to remove this unwanted peak, and the transmittance in the bandpass will be smoother. So we'll see in the next step the optimization from our design. That is the second design. So we increase the number of layers from 12 to 16 layers. As we see here in the green ball, the curve is more better than the first design. As we see, this peak was disappeared. This peak was decreased to 50, and the bandpass transmittance become more smoother than other. This response still need more treatment. So we did more optimization in our design, and we get the last design as in the next step here, also in the green color. As we see, the all unwanted peak was disappeared. The unwanted peak become till 10, just 10. The bandpass transmission become more smoother than other, and the unwanted peak here, all of them was gone. Now the response of the filter become more better and smoother. After we complete the design, we did manual adjustment for our design. So we remove all layers with 9 nanometer in thickness and 10 nanometer in thickness. We try to reduce the number of layers to be the fabrication will be more easy than other. So we need to remove this layer. So we reduce the number of layers from 75 layer to 48 layer or 46 layer. But the response become not that for the 75 layer one. Become more than the design become less than other. The response was decreased, but it's still acceptable. Here we examine our design with another program. As we see before, we make the design for thin film calculation software. So we work in another software called Essential MacLeod to examine our design. So we take the parameter from the thin film calculation software and put it in the Essential MacLeod, and we see the response. So we see the response is totally compatible between the two softwares. That means that the design is okay and working fine. As we see here in the yellow one is the for thin film calculation response, and the green one is the Essential MacLeod response. So we can see that the compatibility reached to 28%. After we complete our design and we investigated it in another program, now we will see the design analysis on our design. So here is the admittance for the filter. We see here is this point is represented each layer, and we see the admittance for each layer. Here we can see the distribution for the electrical field for the infrared filter. As we can see here, represented this line represented the number of layers, and we can see the electrical field in each layer and the distribution for the infrared in general. Yeah, this picture is obtained the absorption for the filter. Our filter is working with refraction or reflection, not for the absorption. And this picture explain that the filter not observe the light. So if you see that the absorption is 0, that means this filter not observe the light while it's reflected the unwanted light. Here we can see the reflection and the transmittance. As you see, is our transmittance, our response for the filter, and this in yellow, red, in yellow color that it's represented the reflection for the filter. As we can see here, the filter is reflect the light instead of observe it. Our design was working with 0 incident light. So incident angle, but the angle may be not in 0 value, must be 5 or 10, 20, any else. Here we can see the filter response against the change in the incident angle. So as we can see, whenever the incident angle is increased, the filter response will become increased also, as we can see in this picture. Conclusion. Here is the conclusion, is very important. As we can see from this picture, we can see this is the transmittance for the wanted band. And this is transmitted this one and this one, this transmittance for the unwanted band. So our design will be to increase this one and decrease this one. So whenever the number of layer increase, so the response for the wanted band, for the band pass is increased. As we can see here, when in the 12th layer, the transmittance for the band pass will become 80%, while when the number of layer becomes 16, the transmittance become 81%, while the number of layer becomes 75 layers, the transmittance become 90%. So whenever the number of layer increase, the response filter become better and better and better. Thank you for listening, and I am ready for any question.
Thank you for your presentation. Dear participants, do you have any question about this paper?
Thanks.
Okay, no questions. Thank you again. I wish you success in your career.
Thank you.
Yunus Al-Safar.
Thank
Next paper belong to dear Zahra Sabbar Lafta. Are you ready to present? Dear Zahra Sabbar Lafta, can you hear me? Dear Zahra Lafta, are you ready to present? Okay. The next paper belonged to dear Alexander Milov. Are you ready to present? Dear Alexander Milov?
Yes,
Can you
yes,
hear
yes.
me?
I'm here. I'm ready.
Okay. Okay, okay. Dear Zahra Lafta, are you ready to present?
Yeah, I am ready. Sorry.
Okay.
Yeah.
Dear Alexander Milov, sorry, Zahra Lafta is ready.
Yeah, I am ready. You hear me?
Okay, okay, okay.
Okay. Hello, my name is Zahra Sabar Lefte, and as you may know, I am happy to present my presentation of privacy preserving homomorphic encryption in cloud storage. With the growth in the application electronic document management, EDM, in the public administration bodies, as well as in the private sector, the need to mention the integrity of information has become even more necessary. Sorry, I have problem in my, sorry. Okay, that use of need.
Sorry, you have 10 minutes, okay?
Okay, okay, thank you. That use information need investment of organization IT transfer home over for the use clause mainly does legal requirement. It is necessary to ensure that integrity of storage file can be permitted mentioned. Current works addressing the verification of the integrity of file storage in the cloud despite present integrated solution for the domains for which they are developed. When analyzed individual for the short-sum aspects such as high computational cost or the use homomorphic syntactic encryption or by the need reflects the file as well before perfection. Considering the problem that still exists and exploit above, it is necessary to study available technology and develop proposal for protocol which allow file use permanently, monitor the integrity through the service specialized in the integrity check provided by third parties, low computational cost and capable of redundancy. Materials. A cloud computing. The cloud as natural evaluation of traditional data mentioned, which distinguish themselves by over computational resources such as storage, processing, and managed application through satellite web service. As show the figure, internet, the example about the cloud computing. B. Cryptography. Cryptography is a study of mathematical technology used to transform readable information into unreadable data. Encryption allows the storage or transmission of sensitive information over secure networks such as the internet, such as connect be ready by anyone except the states. The method that transforms plain text high is content is called encryption. The non-readable content obtained by transformation the clear text performed by encryption process in called ciphertext. C. Process method confidently can be achieved by applying cryptography solution known as the Advanced Encryption Standard AES encryption algorithm. However, ensure integrity is still a challenge. There are several research papers detail the check integrity file. As a result, this researcher proposed different approaches to allow client to verify the integrity of their file, among which the application homomorphic symmetric gravitygraphy use some of the coding has algorithm. Third-party coding and the use challenge can be highlighted. To carry out operation encryption, banking data without decryption, then we need cryptography capable to perform addition, subtraction, and annealing, also multiplication of confident of the fixable variable rate. For our hybrid application, which integrate the two homomorphic cipher, RSA and pillar, we need optimal key size which overall the best processing time, encryption, editing, and multiplication of cipher and decryption. The choice of the optimal size, the key to use, is very important, taking account decryption which take place locally in the computer of the company. Now, in the size of text by encryption does not exist 1 kilobyte full name account number. This work demonstrated that it's possible to guarantee and adequate level and data security and private and user application deployed in a cloud computing environment with the proper use encryption scheme other security machines. The solution present come from the hostable surface, the main thread we are most recent and advanced solution presented by the academic community in the reference literature in the area. Thank you.
Thank you for your presentation.
Thank you.
Dear participants, do you have any question about this paper? Okay, no question. Thank you again. I wish you success.
You are welcome. Thank you.
Okay.
Thank you. Thank
Dear
you.
Alexander Milo, are you ready to present?
Ready.
Okay, sorry. You can start your presentation. You have 10 minutes, please.
Yes, not more, 10 minutes. I understand. I am Alexander Milov. I am a professor of cybersecurity department of National Technical University, Kharkiv Polytechnical Institute. And in my presentation, I'd like to present my viewpoint of cybersecurity system controls as a social cyber-physical system and propose new approach for this problem. Problem is situational control of cybersecurity in social cyber-physical system. First of all, it's necessary to define what is a physical cyber-physical system and social cyber-physical system. One of the achievements in the field of digital transformation of industry is the creation of the environment in which people work in close cooperation with intelligent information and communication system called cyber-physical system. Social cyber-physical system inherit the characteristic of CPS as a complex non-linear system and include a person in their composition. Social cyber-physical system can be considered as a complex social technical system with unpredictable behavior in which social and technical aspects are strongly intertwined. As a formalization of this system, social physical cyber system is defined as a system where CS is a cyber system, PS is a physical system, and SS is a social system and composition of these sets. And this sets containing cyber components, physical components, and social components, respectively. Atomic social physical system is one that is strictly composed on one cyber, one physical, and one social system. And what's the relation about relation? RC is a relation of cyber. Space cyber virtual relation refers to the percent of an information flow, control, or sharing of computational node between or within systems, subsystems, or component. And RS is a social relation, refers to the flow of information, transfer of knowledge between the social components. What is the basic properties of this system? The list of the main properties of cyber system are following. First, the system contains a large number of components. B, the attributes of the components are not predetermined. C, the number of interactions between components can be extremely large. The functional interactions between components are poorly organized and can be confused. Components can work autonomously and set their own goals. The behavior of the entire system is probabilistic and can be highly non-linear. The system interacts with the operating environment is a proactive mode, and on the other hand, can support feedback interaction. And the last, the system understands the context and provide context-driven function. You can see that this basic properties is very maybe sophisticated, is very complex, and there are two types of system: cyber physical system with social component and technical. As for basic properties of social cyber physical system, you can see on the slide, but some words: the complication of technologies process of all level of production and the emergence of large enterprises. The closer participation of people in such intellectual environments provoke the need to apply new ways to manage them, which should take into account not only the features of social cybersecurity system, but also ensure the safe functioning in the face of growing number of complexity, cyber attacks, and the mentioned system. The basic properties of social cyber physical system are listed on the slide, and they include such properties as uniqueness, absence of a formalized purpose of existence, lack of optimality, dynamism, incomplete descriptions, free, real, and some others. You can see the short description of these properties on the screen. These features significantly distinguish the mentioned system from the traditional system characteristic of the classic control theory. What is a traditional control theory, which grew up on the previously existing theory of automatic control. This conservation law object is focused primarily on objects of physical nature and deals with such objects for which the control procedure in its most general form is presented as shown on the slide, where X is an input vector, Y is output vector, W is a disturbances vector, and U is control vector, and two relations between them, F and he. The general chart of the solving the control problem, as we say about the situational control, we have a very different scheme. For instance, a description of the current situation that has developed, the control object is fed to the analyzer input to determine the need for iteration in the control process. If necessary, the descriptions of the current situation is sent to the classifier. The classifier assigns the current situation to one or more classes which correspond to one-step solutions. This information is transferred to the correlator, which store an all-elementary management decision. The correlator determines which of them should be used. If there is only one such rule, that it's used for execution. If there are several such rules, then the choose of the best of them is made after processing preliminary decision in the extrapolator, after which the correlator is used, a decision on the impact of the object. If the correlator of the classifier can't make a decision on the incoming description of the current situation, then the random selection block is triggered and one of the influences that have a small impact on the object is selected, or the system refuses any impact on the object. This suggests that the control system doesn't have the necessary information about its behavior in this situation. The control methods we proposed to be used to control cybersecurity system is based on the concept of situation, the classification of situations, and their transformation, and is methods of situational control. The methods of situational control have characteristics that significantly distinguish them from the method of classical control theory. These characteristics should be taken into account when constructing situational control system and switching to them from system of classical control theory. These features include design costs, situational description language, text and relation, situation classification, control decision, heuristic, and multi-step solution. Some of them is new and non-traditional of control process and require new approaches for its development. First of all, it's a situation descriptions language. This language should reflect all the main parameters and relationships necessary to classify this description and compare it with a control solution. It's necessary to choose the right level of description, which should not be too detailed or too raw. Secondly, its situation classification. Classification of situations occurs of a subjective basis. Classification procedures should be designed in such a way that the classification itself would be suitable for those current situations about which the system has not received the information from expert. And a conclusion, we claim that first, the features of social cybersecurity system dictate the need of revised traditional management methods and transform the management system in such a way that it takes into account the presence of a person both in the control object and in the control loop. Second, as an approach, the use of situational control mechanism is proposed. The feature of this approach and its comparison with existing methods of situational awareness are presented. This comparison has demonstrated wider possibilities and scope for management social cyber physical systems. Third, the application of methods and mechanism of situational cybersecurity control with require consideration of a wider class of type of relationship that exists in social cyber physical system. It indicates that such consideration can be based on the use of so-called pseudo-physical logics considered in situational control. And fourth, situational control based on control by precedence of situations leads to the need to design a classifier of situation primary in cyberspace instead of traditional classifier of threats and intruders. Thank you for your attention. That's the end of my presentation. Thank you.
Thank you for your presentation. Dear participant, do you have any question about this paper? Okay, no questions. Thank you again. I wish you success in your career.
Thank you.
Alexander Milov. Okay, next paper belongs to dear Suraya Yaqub.
Yes, I'm here. I hope you can stop sharing so I can share my PowerPoint.
Okay. You can share your screen now.
Thank you.
You have 10 minutes, please.
Yes, thank you. Assalamualaikum warahmatullahi wabarakatuh, and a very good day. My name is Suraya Yaqub, and I'm with my colleague Zaiful Ashraf, my students, Dr. Ruslina and Dr. Farawani. We are from University Technology Malaysia, Kuala Lumpur. So our topic today is actually a review for visual analytics methodology. Okay, basically currently what we have to do in the visual analytics world, when we develop the visual analytics, we use the basic concept of the GRIPS-DM, yeah? So this is basically like base for everything. So they have 6 parts within that methodology, which is we start with the business understanding and then data understanding, data preparation, exploratory, validation, and then finally the visualization. Okay, so basically this is the methodology that we use within the visual analytics world nowadays. So for us to within this as-is methodology, we found that it is still lacking on certain things. So for us to develop a new methodology or to propose a new methodology within the visual analytics process, we intend to do the review, the systematic review for the all the related methodology that we can use, yeah, within this visual analytics. So for that, we try to look the methodology from 3 perspectives, which is the perspective 1 is from ICT related methodology. So here, we every methodology that we try to review or to analyze or to compare, we compare according to 3 elements, which is the first one is human, the second one is computer, and the third one is reality. So all the 3 perspectives we compare based on these 3 components. So for the first perspective on ICT related methodology, yeah, when we compare it, we compare 3 most significant ICT related methodologies within this ICT world, which is first is SDLC, software development lifecycle, second is DevOps, and third is Agile. Okay, basically
Okay. Dear Suraya Yaqub, can you hear me? Maybe connection is corrupted. Let's wait a while. Dear Suraya Yaqub. Okay.
Okay, can you hear me?
Yes,
All
please
right,
try
then.
again. Okay.
Okay, let me share with you the line again. So sorry for the interruption. Okay, so basically that is all.
Please try your
Used as our core
you
right
can
now.
stop your camera.
Oh, you cannot see me right now?
Yes.
Can you see me right now? I am waving my hand to you.
Yes.
Thank you. Okay, so I think it's okay, right? So can we continue?
Yes, please.
Thank you, thank you. Okay, so on the second perspective, we look for the CRIPS DM first. Yeah, CRIPS DM is actually our core. So even though CRIPS DM, they have the wide coverage for the reality, computer, and human perspectives. But the thing is, even though they have some depth, especially on the computer perspective, yeah, especially on the data preparation and modeling, and especially on the deployment, but they still have a shallow depth of the coverage in terms of the business understanding. So that's why we think that even though we use the CRIPS DM is still not sufficient to facilitate or to guide us within the visual analytics development. That's actually one thing. Another thing is actually they don't have a loop. Yeah, they don't have the alignment or the interconnection between the output from one phase to another phase, or from one process to another process. So basically that interconnection is very important. Yeah, from one phase the output, so how we need to do or how to conduct to other phase is actually very important. So that is actually the number two shortcomings. And the number three is actually no analytics specific tools, device, apps, and techniques, or like a process and procedure has been mentioned within this CRIPS DM. It is very general, so the developer need to find the tools, the proper tools by themselves. So that is actually on the CRIPS DM. Okay, then we look at the Assume DM. Actually, Assume DM is actually the advance of the CRIPS DM. It is on 2016 by IBM. CRIPS DM is 2000, in the year of 2000, I think. So it is 22 years right now. Yeah. So we have Assume DM, and that has been improvised on 2016. Yeah, we can see that Assume DM has improvised, especially on the feedback loop. If you can see here, they have a feedback loop, but they still not cover the infrastructure operation side of PVA implementation. No template, no guideline, even the tools and the facilitation that they intend to provide is somehow the developer don't really cannot grab it. Yeah, but the thing is actually the template. The template is the thing that really can help the routine job. Yeah, so that is actually the weaknesses or the shortcomings of the Assume DM. And next, we also review on the KDD, yeah, knowledge data discovery. So this is actually on the KDD, even though they have a few of feedback loop, but it is still very little, and that is very focused on the computer part. No coverage on the human, or no coverage on the reality part. Yeah, that is on the KDD. Same goes with the SEMA. SEMA, they are really covering on the computing part, but not much on the human and reality part. And the thing is, SEMA, they are really straightforward, and it is more like an exemplary. Okay, so when you have a big project which is you cannot just give a shot, or you just cannot try an error, so it is not suitable for us to use SEMA. But for small project is okay. Okay, the number three is the number five actually, TDSP. So TDSP is actually for the data science process. Yeah, they have a very good coverage on these three process. They have the business understanding, and I think I also love it, especially on this on this computer part, which is they have the data acquisition and understanding, and they relate back with the feature of engineering and modeling. And then after that arrangement, they deploy and they have the customer acceptance at the end. Okay, so basically, we can see that data TDSP is quite a comprehensive methodology that we can use now, but still they are lacking of the feedback loop. Yeah, and they also don't have any template to guide us on this. Okay, so basically on the big data and analytics, we reviewed that 5. And another 5 is basically when we are focusing on the visual analytics as a visual analytics. Yeah, so within this field, we can see that the coverage is basically, if you can see the pattern, is more on the human part. They are covering on the data visualization and interaction, covering on the output and data visualization specification, something in the blue, yeah? But they are very lacking in the computer part. It is a very shallow, very surface about the data processing to the data analysis, no modeling, no tools, no preparation. So they don't really touch about it. Okay, especially now when we are going from the visual analytics to the predictive visual analytics, this component of modeling and computerization is very critical. So that's why we think that even this current visual analytics process is lack in computer part, yeah. And a certain of it, especially on the reality, it is also quite lacking. They have some element of touching about the reality, like a problem characterization, understanding the reality, or have the question, yeah, BQ, business question to people, but they don't really have the systematic template or systematic process or procedure to do that. Okay, so when we are doing the big project, so yes, we will have a trouble in the beginning. So that is actually, we think that still not sufficient for us to have this methodology to cover us. So based on the perspective 1, ICT related, perspective 2, which is on the big data analytics, and perspective, there is some strength on certain methodology and some weaknesses on the certain methodology. So what we can say is, from the sufficiency, we can say that if we want to rely on only one perspective or methodology to really guide us on the visual analytics, it is still not sufficient. Yeah, but we can do that by taking a bit here and there methodology to guide us. But for the big or the systematic project, with us having 2 or 3 methodology within one project, sometimes very confusing. Yeah, especially on the people that work on it. All right. So in terms of sufficiency, we think that we still need a proper methodology for visual analytics. That is actually on the sufficiency. On the depth, as I mentioned, there is a coverage of the process at the sufficient level, but they need a depth in terms of tasks, in terms of tools, guideline, template, and also expected outputs. And the number 3 is actually the alignment between the interconnection between perspective and processes. And finally, something that we not touch here is actually the project management thing. Even the alignment from the design and the process of the visual analytics with the data back to the process of the managing of the project is also one critical factor that we need to consider when we want to develop the methodology for visual analytics. So far, yeah, I think that's it, my presentation. I thank the chairperson, and sorry for the interruption just now. With that, I thank you and pass back the floor to you, Mr. Chairperson. Thank you very much.
Thank you for your presentation. Dear participant, do you have any question about this paper?
Yes, if you have any question, yeah, please drop by now, or if you have time later, you can contact me via the email that have been published in the paper. Thank you very much.
Okay, thank you. No question, I guess. Thank you. I wish you success in your career.
Thank you.
There's
Thank
a
you.
question in the chat.
There's a question in the chat. Let me see. Okay, thank you. Is visual analytic methodology for offline usage or may be used in the real-time usage? thank you, Alexander, for the question. Yeah, basically it is on the offline. But if you are asking about the offline or online or real-time data, yeah, so we try to cater for the real-time data because nowadays with the 5V, right, another one is velocity. So we really need to cover that on the real-time data. So the methodology is supposed to have the capacity to cover that kind of situation. Thank you very much. Yeah, I think this is also give some idea to me, Alexander.
Okay, thank you. Thanks for your presentation again. I wish you success in your career, dear Suraya
Thank you.
Yaqub. Okay.
All right. Okay, see you.
Okay. Dear,
I will stop
dear,
sharing.
okay. Dear Ayman,
Yes, I'm here. Thank you.
are you ready to present?
Yes, I am.
Okay. If you want, you can present your presentation.
Okay, good morning, Mr. Chairperson.
You
Good
have
morning,
10 minutes,
participants.
please.
Thank you. Good morning,
Okay.
everyone. My name is Ayman Salah Abbas. I'm professor of mechatronics and robotics at the British University in Egypt. This paper is being presented on behalf of myself, my colleagues, shown in the title slide who work with me in the department. The title of our presentation is Development of a Soft Gripper Using a Non-Fluidic Compliant Mechanism. I will first identify why is this a problem and the aim of this research, followed by a summary of the literature review, and then the methodology of our research will be discussed, and the design and material selection will be presented graphically, and then the results of our research and discussions with experimental work, and then I will conclude my work. Robots with end effectors traditionally have been made with non-compliant mechanisms, which means that they open and close to a fixed angle, and they are generally made of rigid material, which is not suitable for many applications, especially in agriculture, as you can see from the figure here. Not that many research and commercial robots are available where you can have a force-sensitive gripper which grips the object to be carried depending on the nature of its surface and its weight and its volume and so forth. This results in damage, conventional mechanism results in damage to the objects that are picked up by conventional grippers. The earlier solution was to use fluidically actuated compliant mechanisms, such as pneumatically actuated grippers, but the problem is they are complex in terms of control and in design and in operation as well. Therefore, our aim is to develop also a soft gripper, but it has to be a compliant mechanism and it also has to be non-fluid, so it does not use pneumatic or hydraulic actuation to achieve the compliance of the gripper to the object being held. Oops, sorry. The literature review identified that there are three classes of non-fluidic actuators. These are smart material-based actuators, or single input, single output actuators, or linkage-based actuators, and I will review each class in the following slides. The first class of non-fluidic actuators are those made of smart material. The most successful designs have been the two presented in the figures on the right-hand side. The first one by Shi et al., and that was more than 10 years ago, was developed to be used in surgical operations where a material that reacts to small voltages resulting in bending of the actuator enables us to control the flexure of the gripper without damaging, obviously, in a surgical operation, the internal organs of the person being operated upon. Another example, like the figure in the bottom right-hand corner of the screen, was made of shape memory alloy. These are materials that expand and contract differently depending on the temperature, which results in a phase transformation of the material. And the heating and cooling is achieved by applying a small microvolt. This particular design shown here enables the gripper to, on the bottom side of the screen, enables the gripper to adapt to the curvature of the object regardless of its size and regardless of the material it's made of. These are examples. Further information can be found in the paper, obviously, of this class of non-fluidic material. The second class are those that use a single input and single output actuator, where you have generally a small motor either directly causing us input that results in several outputs, or sometimes you might have cases where you can manually operate the input. We have two examples here out of the literature review. The top right-hand side illustrates an example where you have a motor and a compliant mechanism made of polymers. And when the motor starts to rotate, it's transformed into a linear motion, which opens and closes the gripper from the top side of the mechanism. But the design of the shape allows it to conform to the object being held. The second example is the iris design, which is shown in the right-hand side, bottom side of the screen, where it looks like the iris of an eye. Again, it's made of a polymer material, but the input is directly rotation without any transformation. And the design kinematically allows these beams inside to flex and therefore adapt to the geometry of the object being held. This existing design 4 years ago suffers from a problem is that it's only manually operated, which is obviously not economical or cost effective if you want to use it in a mass production robot. The third class of non-fluidic actuators are those that use kinematic linkages. And we have 3 examples here. The first example is basically an adaptive soft gripper with multiple inputs and outputs shown in the figure with the black background, with a white glove-like hand, where you have a separate actuator, electric actuator for each finger, and you have the microcontroller and the driver controls how much each finger flexures or bends to adapt to the object. It's very similar, obviously, to the operation of the human hand, but the problem is, obviously, is the complexity of control and is prone to errors. If the sensors detect something wrong, then you might cause damage to the object being gripped. The second example is the one on the top, where a hand, again, is made from polymers, 3D printed polymers, and we have a mechanism. But again, each half of the design has a separately controlled motor, as you can see here in figures C and D, and they are controlled independently to achieve the compliant required action of the gripper. Again, complexity is a major issue and it's prone to errors. Even with a feedback control, you might encounter a case where the gripper might damage or actually might cause the object to slip if the gripping force is not enough. And that's a major issue if you want to commercialize such designs. The final example of a linkage-based actuator is shown on the right-hand side towards the bottom of the screen, where we use, or the authors used, a statically balanced mechanism. So under unloading conditions, it's statically balanced using a simple 4-bar mechanism on each side. And it's preloaded by opening the gripper through a pulling action. This pulling action indicated by the red arrow at the bottom of the figure, C here, might be electrically actuated or might be actuated by a pneumatic or hydraulic. But again, that means you have additional control for the pneumatic or hydraulic, which we don't require due to the issues I stated earlier. So normally this design would be actuated by an electric linear motor or a normal motor with transformation from rotation to linear motion. Based on our literature review, we identified that a more novel approach would be to combine the IRS with the 4-bar mechanism. So we are going to follow an iterative approach where we take the initial design of the IRS, identify the parameters that need to be optimized, conduct a finite element analysis using ANSYS software, find the optimum design geometry, conduct a kinematic analysis to operate mechanically the IRS rather than manually, fit it into the robotic arm, and then fabricate the sample and test it with various objects. In terms of design of the material, we basically focused on 3 aspects: the material selection, the geometry of the beams inside the IRS, and how it operates, which is the gear kinematics. The material selection, we selected PLA, polylactic acid material, standard 3D printing material that works on most 3D printers. The reason we selected this particular material, in addition to its low cost, is that it has a relative high flexural strength, which is an important property required for any compliant mechanism. Because if you have a too rigid, you don't get the required compliance, and if it's too soft, you don't get enough gripping force. And the properties of the particular PLA we used are shown on the table on the right-hand side. I would like to bring to your attention a particular property, which is a flexural strength, which is 83 megapascal. As I will refer to this value later in the presentation. The second aspect of our design is to optimize the geometry. Our design is different from the IRS in the literature, that it's formed of 2 layers, as you can see in the middle figure of the screen. We have 2 layers where each layer has a series of bent beams as shown on the right-hand side figure. We have a series of them, but only one is shown for simplicity to illustrate the complexity of the geometry. And we have the same design on the lower second half, but flipped by 180 degrees. So for each corresponding beam, you will have another one rotated by 180 degrees in the lower layer and vice versa. They are fixed together using PLA pins at the end of each pin. This compliant beam shown here, the curved beam here, is the basic building geometry, which is repeated. And therefore, we need to optimize this to see how much force and gripping force without slipping we can achieve. We conducted a finite element analysis, and the result was an optimization of thickness 2 millimeters and width 5 millimeters, and the curvature is close to an ellipse, the major axis. This is the whole design, as you can see in the figure, of the 2 rings with all the beams, as you can see very clearly. Once they start operating together, you get basically the IRS effect in the middle here, but only with a single mechanical input. The outer ring of the top layer is made into a spur gear, and it's driven by a directly coupled pinion, as shown on the left-hand side of the figure. So when you want to operate the gripper, you basically turn on the small DC servo motor here, and due to the large gear ratio, it opens and closes slowly, which avoids damaging the object being held, and the beams flexure or bend according to the volume and the weight of and the surface material of the object being carried, with the same input of the motor without having any control. So the control is just a simple on-off command. Again, we optimized not only the beam, but the required dimensions and geometry of the whole iris. We came from the kinematic study with an optimum diameter of 120 millimeters for most objects, especially that might be used in a commercial setting, and a diametral pitch of 116 modular 1.5 and a ratio 5. From the motor fixed to the pinion, and it only requires 0.12 Newton meter, which is reasonable. Of course, motor nor most a lot of energy. This is the final design of the iris mechanism with a cover plate, as you can see here, and here it is fitted to the robot as a 3D model, but we'll see in the next slides the actual experimental run. Here we can see the figures of the analysis of the iris design, the complete iris design, and as you can see, the maximum stress is 33 megapascal compared to the 83 megapascal strength of the PLA. So we obviously are way far from the maximum and even far from the yield, so no plastic deformation occurs resulting from the repeated operation of the opening and closing of the iris. The angle is very important because otherwise the bending angle of each beam, because otherwise you would not be able to carry small or large objects simultaneously. So these charts illustrate the angles, and as you can see, it's around 90 degrees as measured in terms of maximum stress, moment reaction, and also the total strain energy, which is an important contributing factor. Otherwise, there will be damage to the iris after repeated operation. This is the result of our experimental work. This is the printed PLA iris made of red color PLA, and this is our sample robot with the controller, and it's operated at this prototype stage with a joystick, but obviously can be fitted into a complete control unit where it operates automatically once the object is sensed. We tested the prototype with 11 objects to test the gripping force, if it can grip it initially or not, and the size and material as well. We had 11 objects of different shapes, weights, and gripping diameter that can fit inside the iris. We are restricted due to the geometry and the size of this particular prototype to a maximum diameter of 50 millimeters. As you can see here, we can see the results of the different objects. 9 of the 11 objects were successfully gripped without damaging them and without slipping them. The only 2 that were failing were 8 and 9. Number 8 was because it's smaller than the size of the aperture of the iris when it closes. It's still thinner than the size, and the other the opposite because it was too large for the opening of the iris. In conclusion, we have managed to design a compliant mechanism which can be actuated with a non-fluid actuator, which reduces the complexity of the control system. It's just the developed actuation mechanism because it just relies on an on and off control. It's simple and very reliable, not prone to errors. The maximum aperture opening for the iris in this particular prototype is 50 millimeters, and the minimum, but obviously a similar study can be conducted if you want a larger or smaller design. We have tested with different objects with different volumes, weights, and shapes, and most of them passed. Only the 2 that did not pass the experimental work were those where the size was too big or too small for the aperture opening. We managed to carry objects up to a weight of 125 grams without slipping. The two objects only failed because of the size, not due to the material or the weight. And that's stated in detail for the last 2 points. Thank you for your attention. I'm open for any questions. Thank you.
Thank you for your presentation. Dear participants, do you have any question about this study? Okay, no question, I guess. Thank you again. I wish you success in your career.
Thank you so much. Thank you.
Dear Ivan Garcia Martinez, are you ready to present?
Yes.
Okay, you can start your presentation if you want, if you are ready. You have 10 minutes, please.
Can you guys see my presentation and hear me okay?
Yes.
Perfect. Hello, everyone. My name is Ivan Garcia. I'm going to present, it's a pleasure for me to present the work of evaluation of cognitive workload in automated drilling processes for aerospace structures. I am representing the Technological Institute of Aeronautics in Brazil, where I pursue a doctorate degree. And currently I'm located in Japan, working for the Boeing company as an R&D engineer. And thank you for the opportunity again. I would like to share a little bit of the vision. Here we try to have robotic products that are intuitive, easy to use, and responsive to the needs and states of their users. And here I show a broad technology roadmap that shows that the demand on this axis, and we're moving towards more solutions that comply with high mix and low volume. So we need more solutions that are customized for this work, and we're tackling for more complex processes. This work uses the NASA TLX to obtain data of workload survey of 2 different automation solutions that are currently used in production. One, it's an automated drilling machine. Second one is a robotic platform. And we use this model here to identify opportunities and concerns. Here is just for you guys to have a feel of how the human machine interface and the mechanics and operators who use these machines, they see the full day. They're working on an HMI that looks like this, where they can have alarms, messages, process parameters, positions, program, status, and like to share before some unique challenges of the use of those automated solutions and for this application. So first, complex products, a size of the products, the quantity of mechanical fasteners. So here I put 2 numbers that we can have up to 1.5 million to 3 million fasteners in some commercial aircrafts. Also costly products. There's very little room for mistakes. We have lots of customized and complex automated systems that are used for the purpose of completing these structures. Because of the complex products and customized systems, we have a complex operation. We need a high-skilled trained mechanics and operators to use machines, and long operation as well to fulfill large quantity of fasteners, we need people to stay in front of the machine for a long time, and several people working in several shifts. An example here, a process would take from 16 to 21 hours to complete just one structure. For this work, we decided to go with NASA TLX, which provides a multi-dimensional rating procedure for overall workload. And we have 6 subscales here: mental demand, physical demand, temporal demand, performance, effort, and frustration. Here's a good link for anyone who's interested in how to apply this method. And therefore we capture here subjective experience of equipment operators. And one benefit of this method is that does not intrude or affect the primary task of the operators, which is to use these machines to complete the aerospace structures. On the other hand, the subjective measurements are always influenced by context. So ratings can be affected by experiences that were witnessed just before we applied this instrument. And for this work, we worked with 3 equipment operators for one machine and 3 equipment operators for the other machine, full-time equipment operators with years of experience. And we applied this instrument not only once after the complete process was done, but also as several tasks were being completed. So as tools were prepared, as coupons were drilled, as initial setup was completed, as the first drilling process, changing temporary fasteners, and pre-drilling process, and final setup. Here I show the model that we will be using to evaluate the results from the instrument. So stress can't be imposed by having too much to do in too little time. And in addition, fatigue as a stressor decreases performance and creates problems in maintaining attention. And performance first increases to an optimal level. So here you can see demand and performance. And then performance declines as demand increases further. So here we have boredom and exhaustion. We want to be working here. Here I show some results. And these are the results of the drilling machine. I am not going to present all of the results here so that we can comply with time. Here, I'm going to showcase this too. Here when we evaluate the process as a whole, we see that the mental demand is within average, and we see that the physical demand, the average workload, has been rated in the low part of the spectrum. And here I show the results of the robotic platforms, where we see that the mental demand has been rated on the high part of the spectrum. Then we decide to show the results using time and differentiating the processes that were used, so that we can answer the question, what tasks contribute to these specific results. And here we show the results for the mental demand for the drilling machine process. And here we can see that the average mental demand is in the high range for the initial setup. And this initial setup requires input parameters aiming to guarantee that the structure is drilled as expected. And for example, preparing coupons, checking countersink for all these tools, and referencing the machine to the product. Second example that I want to share here we have physical demand. Here we can see that the physical demand, it's in the lower range for most of the drilling process. This can result in this low physical demand may result in boredom. And so we can see that it's not ideal. And here we show the mental demand for the robotic drilling process, where we can see that it's in the high range of the 0 to 20 scale, and this may result in exhaustion and fatigue for the operators here who work on this. Here we bring some recommendations. So results show under arousal for long periods of time for experiment 3, and this may lead to boredom. Here we recommend to update the HMI with predictor displays, aiming to increase the level of arousal. This can include objectives and challenges to support the delivery of quality parts within specific cycle time. Secondly, we show workload over arousal for experiment 6, and this can lead to exhaustion and fatigue. And fatigue is a stressor that degrades performance and create problems in maintaining attention. In this stage, equipment operators monitor repetitive operations of the automated system for long period of time, and we recommend updating the HMI to schedule breaks so that people don't get fatigue, and as well to minimize distractions, such as removing scheduled meetings that are done during this drilling process. And finally, we recommend to focus on a user-centered design of this human-machine interface, aiming to consider the capabilities and the needs of the operators, integrating information in ways that fits the user goals, tasks, and needs. And for conclusions, this work evaluated the workload of experienced equipment operators, confirmed the importance of evaluating workload in different phases of the automated processes, and showed the results where we can have exhaustion and fatigue. And finally, we presented some recommendations for enhancing human performance in these automated processes. There's some reference. Thank you very much. Any questions?
Thank you for your presentation. Dear participants, do you have any question about this paper? Okay, no questions. Thank you again. I wish you success in your career, dear Ivan Garcia.
Thank you very much.
Okay. Dear Ivan Ralev, are you ready to present?
Yes, yes.
Okay, the last paper of the session. You can start if you are ready. You have 10 minutes, please.
Okay. Dear professors, colleagues, and guests, my name is Ivan Ralev. I'm a PhD student at the University of Rusi. Today I'm going to present our paper co-authoring with Professor Georgi Kruslev. The following topic is commands and models of implementation of a hand gesture recognition system. At the beginning, I have to explain what is a human-computer interaction. It determines the way of interaction between the computer system and the person. Classic tools are mouse, keyboard, joystick. The intelligent human-computer interactions realizes this interaction in a new way, aiming to make the human-computer interaction similar to that between human and human. Interaction through gestures, emotions, and various biological indicators of a person refers to the technology of the future. When a programmer decides to use gesture recognition to interact with the program, they need to know the components of the system that uses gesture recognition well. This slide describes the individual components of a system uses hand gesture recognition by computer vision. When a user performs a certain gesture, number 1 from pictures, it must be recorded by means of hardware video device, which can be a simple webcam or specialized one. The recorded data, individual frames containing the gesture, is transmitted to a computer system. which has installed a software development kit. The program code created by the programmer accepts the processed and analyzed results for the presence of a gesture and perform predefined actions. They can be on existing code or a custom developed application by the programmer. In the absence of the SDK or using one that does not provide full and sufficient gesture recognition, the program code becomes more complicated and takes more time to complete the program. Next slide describes a generalized model of the phases that need to be passed in the design and implementation of software application using an intelligent human-computer interaction. In this case, hand gesture recognition. The first step can be considered the conceptual plan for creating an application that achieves a certain goal through certain means. After this is done, the second step is to analyze the available hardware. It is important to clarify that the hardware that will be worked on may not be available at this time. In addition, the implementation itself can be performed on emulators. The third step is to choose the way in which the user will interact with the application itself. The first option is to use mouse, keyboard, joystick, and more, or use intelligent human-computer interactions, gesture recognition, face recognition, emotions recognition, voice recognition, and so on. The last phase is the realization, coding, testing, and implementing the application. The second and third phases can be divided into four subphases when intelligent human-computer interaction is used. As the first phase, it is necessary to select the hardware device with the help of which the input and output signals will be recorded. Such devices may be a video camera, gloves with sensors, helmet, and more. After selecting a device in the second phase, it is necessary to select the programming language through which it will interact with the hardware. The first criterion comes down to what programming language the programmer knows. If they know more than one, it is necessary to make an analysis of which of them provides the best opportunities for implementation and functionality. The third phase, which is optional, is the selection of the SDK. The programmer can code all he needs to run the application, but it is acceptable for a very small project with limited capabilities. The choice of algorithms methods by which the gesture recognition will be performed is the fourth phase. Here you have to make a very good analysis and comparison of the different options. If gesture recognition is used, not every algorithm can be effective and efficient with a variety of gestures. Open source computer video library is one of the most common solutions offering the basic capabilities of the programmer to use gesture recognition in this program, as it contains a huge number of image processing algorithms. Supported languages are C++, Python, Java, and MATLAB. It has a modular structure with individual libraries shared or static. Another SDK is Intel RealSense. This slide shows the hierarchy of the main interfaces that make up the SDK. The session interface can be considered as an entry point, and under its control are the input-output module and algorithms modules. The Sense Manager interface organizes a multimodal pipeline for tracking hands, gestures, face, and more. Start, stops, pause, and resume the pipeline. Sense Manager uses as under the interface Capture Manager, which takes care of the selection of input-output device, camera, color adjustment, depth, and audio flow. During the execution of the pipeline and when the captured image from the input device are processed by the algorithms modules, the information can be transmitted to the interface's face module for tracking and face recognition, hands module for gesture recognition, hand or another interface tracking. The processing of the audio stream is realized separately. The control is performed via the audio source interface, which contains the speech recognition interface, allowing the processing of specific voice functions. In skeleton-based recognition, in this case, the wrist is made up of 22 points in the Intel SDK. The number of points is different for different software libraries. 15 of these points represent the articular connections of the fingers. 5 are located on the finger tips. 1 wrist at the beginning of the wrist and 1 palm in the middle of the palm, which is also used as a control. The left picture shows the location of the points on the palm and their naming. In each of the points is represented in a three-dimensional coordinate system in which shoots. The design and implementation of a hand gesture recognition system requires good analysis and knowledge of techniques, algorithms, and hardware devices. It is important to make the right and accurate choice at the beginning so as not to complicate the subsequent implementation. For great accessibility, it is important for the programmer to consider the user's ability to access certain hardware devices. Thank you for your attention.
Thank you for your presentation. Dear participants, do you have any question about this paper? Okay, no question. Thank you again. I wish you success in your career.
Thank you.
Yes, the first session of the day is over. Dear participants, thank you for your attending. I would like to end the session. I suggest you attend the next session, which will start shortly at 1:30 special session. See you in the next session. Goodbye.
Thank you.